Hi there. In the modestly popular 2-transistor electronic load stroke source video, link should be somewhere above, as I mentioned, it was let down by a serious thermal drift. I continue to develop this further. This video shows an improved 0.1 to 1 amp electronic load stroke source that eliminates that thermal drift issue, and as well as that increases linearity, although it has taken 4 transistors to get there. Now let's go to the setup. First of all, top left hand side, we have the fan assisted heatsink for the TIP122 power Darlington. Moving further over to the right, we have the power supply for the output, and that I've set to 12 volts DC. And then further over to the right, we have a digital voltmeter set to 10 amps DC, which measures the output load. Moving further over to the left, we see the car bulb, and I've attached the 21 watt filament as a load to this circuit. Moving slightly more over to the left, we have the breadboard, and on the breadboard we have R11, which is the current sensing resistor. Then moving finally over to the potentiometer, the small potentiometer, which I believe is 10k, and that takes this circuit from 0.1 amps through to 1 amps. Okay, I'm starting to dynamically test this circuit. You've got the power indicator here, the little red indicator on the left hand side. I'm at the minimum with the potentiometer, which is 80 milliamps, and I'm trying to achieve 0.1 of an amp, and you can see it's a bit fiddly. The potentiometer is a bit small, but it was the only 10k I had. Okay, I've achieved 0.1 of an amp. Now I'm now going up to achieving 1/4 of an amp, and we're nearly there, and that's it, 1/4 of an amp. The linearity has improved over the previous circuit, but it's not absolutely on point, but it's pretty good. And I'm now going for 1/2 an amp load. You'll see the filament of the car bulb not quite lighting up. And there you are, I've achieved 1/2 an amp, more or less. Now I think I'm going for 1/4 of an amp. No, 3/4 of an amp. And we're nearly there. That's it. I think the filament has just started to light up. That's a 21 watt filament. I can achieve 1 amp with that. Yes, that's okay, isn't it? That'll pass muster. Now I'm going for a full 1 amp. And there you are, the bulbs lit up quite a bit, and it will affect the light level on the camera. It'll start darkening, but there we are, 1 amp spot on. So it's doing very well. It's a very stable circuit, this. Using a long-tailed pair. Now that is the maximum current of 1.01 amps. See, it's quite a good range with a little bit over either end. Now I'm coming back down to 1/2 an amp. That's it. And now on to the thermal drift issue that was a problem with the previous circuit, which I've now thankfully eliminated. As we established, the thermal drift issue was caused by D2 getting warm, and it was changing the output. I've set the output here to 1/2 an amp. I've just presented the freeze it can, that's what I'm about to use, and I'm freezing it for all I'm worth. And there's no change on the output, so it looks as though I've solved the problem. I'll change the output to 0.1 of an amp and see how it behaves then. But I'm waiting for the D2 to come up to room temperature. Here we are. I've changed it now to 0.1 of an amp, and let's see whether that's affected by freezing D2. Here we go. No, it's pretty stable. I thought I saw it drop down one digit there, but it's probably the potentiometer causing the problem. I've now moved up to 1 amp, so this is the circuit at full blast, and and that D2 gets warm, and I'm now blasting it with a bit of freeze it, and there's no change, so I consider that a success. Absolutely stable. Okay, just a brief run through of this circuit. There are two supplies, one on the left, which is a 12 volt DC supply, and one on the right, which is the load supply. I haven't indicated the voltage on this battery because the battery could be 9 volts, 12 volts, 24 volts, 48 volts. This circuit doesn't really differentiate between any of those, and in fact the circuit can go down to about approximately 2 volts. Looking at my breadboard and looking at this circuit, there is no car bulb shown, but what I did was replace this fuse here on the output, which defends in the circuit from a reverse polarity of the battery. This diode would start conducting and the fuse would blow, or indeed a fault in the output circuit here might cause this fuse to blow. But in the breadboard I've used that 21 watt element of a car bulb. Moving back over to the left hand side, we've got this R1, which is a resistive dropper, and C1. They behave as a first order filter and drop the voltage down to a Zener voltage, which I've indicated here as 8.7, and I come back to that in a second. But the Zener voltage is made up of D1, which is 6.2 volts, and the forward conduction of this LED. The combination of those two in series produce about 7.9, maybe 8.1 volts. But if you look at this carefully, and the reason why I say that, it's the bottom of the anode, I should say, of the Zener diode is connected to the anode of D2. So as current flows through this circuit, D2 voltage will vary slightly, but the reference between this point here and the supply always remains the same, thereby producing a shunt regulator for the precision of this circuit. VR1 here, of course, naturally controls the circuit from 0.1 amps through to 1 amp, and the two resistors either side of this potentiometer set the upper and lower limits. The capacitor here, C2, just removes any noise that might be produced on this line, particularly caused through the movement of the rotor of this potentiometer, and that will smooth out that voltage for this transistor here, Q1. Q1 and Q2 are a long tail pair, or if you like, a differential pair. If you want the fine details of that, particularly the mathematics of this, I'll put a link in the description below to link you through to the maths of that. If we move on, you've got a capacitor here. Well, that is across the base and collector of Q3, which is the drive transistor for the tip 122 power Darlington, and the capacitor just prevents any possible oscillations that might occur in this circuit. The long-tailed pair Q1 and Q2 I chose to be PNP transistors. In fact, I had a small collection of these PNP, what are they? The BC559C. And I chose two transistors. They need to be reasonably well matched. And I chose these two transistors because their gain was just over 400. And they're both more or less the same. Moving on to the drive transistor, you've got a small degenerative resistor here, small value, just to keep Q3 in stability. Incidentally, I chose the PNP transistors for the differential amplifier, I say, but simply because the collector and the base, the transistors can get very close, millivolts close to 0 volts. If I use an NPN transistor, the base emitter voltage for a start is a disadvantage because it's 0.6, 0.65 of a volt. I wanted to reach down to much lower voltages than that, and so I inverted the configuration and used PNP transistors, and they were able to do the job very well. In fact, I'm constructing here a transistorized, rather simple op-amp. The drive transistor Q3 has in its collector a pull-down resistor, which effectively this collector load is, and that drives the base of the tip 122, which in turn, of course, with the variable control VR1, adjusts the current flowing through this transistor into the R11, which is the low current sensing resistor of 0.94 of an ohm. And then eventually the current flows through D2 as I described earlier. And Q2 of the long-tailed pair base monitors the voltage at that point there, and the base via the variable resistor and R3 effectively is linked to the other side of that resistor. So this circuit only watches the voltage, similar to an op-amp, across this resistor, not across this resistor and this diode, because D2, as we knew with the thermal drift, was a problem. I have a way of visualizing feedback in a circuit, and I'll demonstrate this to you, and I hope it's reasonably clear, but I wouldn't blame you if you found it a bit confusing, but this is how I visualize it. If the load were to increase its current demand, that current demand would flow through Q4, that effectively would make R11 voltage at this point here go high. If that goes high there, the base of Q2 goes high. The emitter of Q2 also goes high. This point here goes high. The emitter of Q1 will go high. The collector of Q1 will go high. And if that goes high, the base of Q3 goes high, which makes the collector of Q3 go low. Should that point at the base of Q4 go low, so the voltage at this resistor at this point here would go low, countering the rise in demand of current from the load. So therefore this operates, as my description, just demonstrates negative feedback. I would just like to add that LED 1 also doubles up as a power indicator. And the other point I'd like to make is that when I mentioned about the various voltages that can be used in different batteries, it's worth keeping in mind the tip 122 is only capable of dissipating about 12 watts. So we need to keep within the parameters of the tip 122 Darlington. And I'll put a link in the description below to the parameters, to the data sheet. Just as an example, if the battery is 12 volts at 1 amp, well, that's 12 watts. If the battery is at 24 volts, it would be half an amp to make 12 watts. And if the battery were at 48 volts, then to achieve a maximum of 12 watts, you're down to a quarter of an amp.